In this journey inside the world of confectionery, we explore how 3 iconic treats are crafted on an industrial scale. From the fluffy nougat and caramel of the Milky Way, to the crisp wafer layers of KitKat and the colorful sugar shells of M&Ms, discover the precision, machinery, and artistry behind these beloved chocolate classics. The story of how a Milky Way chocolate bar is made begins long before the machinery of the factory is even switched on. To truly appreciate the intricacy of this process, it is important to understand that the Milky Way is not a single uniform substance, but a layered and highly engineered confection. At its heart lies a soft, aerated nougat, followed by a creamy layer of caramel, all of which is finally enrobed in smooth milk chocolate. Each of these elements has its own history, its own chain of ingredient sourcing, and its own dedicated stage in the factory. Together, they form a symphony of industrial food science that results in the consistent, fluffy, yet chewy chocolate bar millions of people enjoy worldwide. The nougat base is where production begins, and this is perhaps the most technically complex component of the Milky Way bar. Nougat is essentially a whipped matrix of sugar, glucose syrup, and proteins that have been foamed with air to create a light but resilient structure. In the industrial plant, the process begins with sugar and corn syrup arriving in massive tankers. These raw materials are tested for purity and exact sugar content before being pumped into storage silos. Precision is essential because the texture of nougat depends on sugar concentration and the way that sugar crystallizes during processing. Alongside the sugar and syrup, egg whites or whey proteins are introduced as whipping agents, providing the foaming capability needed to trap millions of tiny air bubbles. Inside the factory, enormous stainless steel cookers are charged with the sugar and syrup blend. The mixture is heated under controlled conditions until it reaches the correct temperature to dissolve fully and create a smooth syrup. At this point, the syrup is transferred to high-capacity planetary mixers. Here, the whipping agents are added, and powerful mechanical beaters begin to churn at high speeds. Simultaneously, compressed air or nitrogen is injected to encourage aeration. The transformation is remarkable. A thick syrup turns into a voluminous, marshmallow-like nougat with a soft bite, yet enough structure to support further layers. The flavor of the nougat is carefully tailored during this stage. Milk powders, cocoa, and small amounts of fat are added to create the signature taste that consumers recognize instantly. The balance between sweetness, dairy notes, and a slight cocoa undertone is adjusted using computerized dosing systems. Once the nougat has reached its ideal texture, it is discharged from the mixer onto a continuously moving conveyor belt. The mixture is still warm and pliable at this point, so it can be spread into a uniform slab by automated rollers and calibrators. This slab, which is often several meters wide, will form the base layer of thousands of bars once cut. Once the nougat layer has set to the proper firmness, the caramel layer is applied. Caramel production in the factory is itself a separate process. Large vacuum cookers are used to heat sugar, glucose syrup, milk, and fat until the mixture undergoes controlled caramelization. The result is a rich, golden mass that develops both sweetness and complex roasted flavors. Because caramel can harden quickly, it is produced continuously and deposited directly onto the moving sheet of nougat while still fluid. Automated depositing heads spread the caramel in a consistent thickness across the entire surface, creating a glossy, sticky layer that adheres perfectly to the nougat base. Cooling tunnels equipped with chilled air currents then stabilize this caramel layer so it achieves the desired chewy texture without oozing during cutting or enrobing. The combined sheet of nougat and caramel now travels toward the cutting stations. High-speed guillotine knives slice the slab first lengthwise into strips, and then crosswise into individual bar-sized pieces. Each bar is precisely measured to ensure uniform weight and dimensions. Advanced vision systems often inspect these pieces as they move along, rejecting any that deviate even slightly from specification. The bars are aligned neatly on conveyors, preparing them for their most visually dramatic transformation, the chocolate enrobing process. Enrobing is the stage where the bars are fully coated in a curtain of liquid milk chocolate. The chocolate itself is prepared in a different section of the plant, where cocoa mass, cocoa butter, sugar, and milk powder are blended and refined. Industrial refiners crush these particles to an extremely fine size, usually below 20 microns, to produce the smooth mouthfeel associated with premium chocolate. The chocolate mass then undergoes a process called conching, where it is heated and stirred for several hours to develop flavor and remove unwanted acidity. Before enrobing, the chocolate must be tempered, a precise heating and cooling sequence that encourages the formation of stable cocoa butter crystals. Proper tempering ensures that the final chocolate coating has a glossy finish, a satisfying snap, and resistance to blooming, which is the unsightly whitening that occurs when cocoa butter separates. At the enrobing station, the prepared chocolate is pumped into a flowing curtain. The nougat and caramel bars pass underneath this curtain while riding on a wire mesh conveyor. As they move through, chocolate cascades over them, fully covering the bars from top to bottom. Any excess chocolate drips away through the mesh, ensuring that each bar has an even but not overly thick coating. To complete the coverage, additional chocolate is sprayed or deposited onto the underside of the bars. Small vibrating mechanisms and air jets are used at this stage to knock off any lingering drips and to smooth the chocolate surface. Following enrobing, the chocolate-coated bars enter a cooling tunnel that stretches many meters in length. Inside, chilled air circulates at carefully controlled humidity to gradually set the chocolate. Rapid cooling is avoided since it could cause cracking or poor crystal formation. Over a period of several minutes, the bars emerge firm, with a perfectly sealed chocolate shell encasing the caramel and nougat layers. Once cooled, the bars are ready for wrapping. Modern packaging lines for Milky Way bars are feats of engineering in their own right. High-speed flow wrappers feed a continuous roll of printed film, which is cut, folded, and sealed around each bar as it passes through the line. Heat-sealing jaws close the wrapper ends, forming the familiar tight package with branding clearly displayed. Many factories operate these lines at astonishing speeds, sometimes producing hundreds of bars per minute. The wrapped bars are then grouped automatically into multi-packs or cartons, depending on their final market format. Quality assurance is interwoven into every stage of the process. Samples are pulled at regular intervals to test for weight accuracy, texture, flavor consistency, and packaging integrity. Metal detectors and X-ray scanners check that no foreign objects are present in the product stream. Sophisticated sensors monitor the viscosity of caramel, the density of nougat, and the temper of chocolate, adjusting parameters in real time to maintain uniformity. These measures ensure that the consumer experiences the same taste and texture every time they open a Milky Way bar, regardless of which factory produced it or which country it was made in. Once packed, pallets of finished bars are wrapped in protective film and moved to temperature-controlled warehouses. From there, they are loaded onto refrigerated trucks for distribution. Maintaining a stable climate during storage and transport is crucial because chocolate is highly sensitive to heat and humidity. Logistics systems track inventory carefully, routing products efficiently to supermarkets, convenience stores, and vending machines around the world. The journey begins with the wafer, which is at the heart of the KitKat's crisp texture. Wafer making in a confectionery plant is very different from baking cookies at home. Industrial wafer production relies on automated lines with massive rotary baking ovens. The basic batter for these wafers is composed of wheat flour, water, sugar, vegetable oil, and small amounts of leavening and emulsifiers. Ingredients arrive in bulk form. Flour is delivered by tanker trucks and pumped into sealed silos, while oils and syrups are stored in large stainless steel tanks. Automated dosing systems measure exact quantities of each ingredient, blending them in high-speed mixers to form a smooth, pourable batter. This batter is then pumped into wafer baking plates. These plates resemble oversized waffle irons, sometimes several meters long, and arranged in continuous carousels or tunnels. The plates close on the batter and pass through gas-fired ovens, baking the mixture into thin, crisp sheets that are both light and strong enough to hold their structure under chocolate. The process requires delicate timing. Too much heat and the wafers become brittle or scorched. Too little and they fail to crisp properly. Once baked, the sheets travel along conveyors to cooling racks, where ambient air helps them stabilize before the next stage. Once the wafer sheets are ready, they are cut and layered with a chocolate-based cream filling. This cream is made by combining sugar, milk powder, and cocoa mass with a fat component to create a spreadable paste. Interestingly, in many factories, offcuts and broken KitKat wafers from earlier in the line are ground and incorporated into this cream mixture, ensuring nothing goes to waste. This reuse not only reduces waste, but also contributes to the distinctive taste and aroma of the filling. The cream is applied evenly across the surface of the wafer sheets, after which another wafer sheet is pressed on top, forming a multi-layered sandwich. Typically, a KitKat core consists of 3 or 4 wafer sheets with cream between them, giving the bar both crispness and a pleasing bite. These layered sheets, sometimes referred to as wafer blocks, are stacked to a considerable size, cooled, and then sliced into the precise dimensions required for KitKat fingers. Precision cutting machinery, equipped with guillotine blades, ensures that every bar is exactly the right width and length. The cutting step is one of the most visually satisfying moments on the production line, as enormous blocks of wafer and cream are transformed into neat rows of bar-shaped fingers, ready to be coated in chocolate. Now comes the enrobing stage, which transforms these wafers into the familiar KitKat bar recognized worldwide. Before coating, the wafers are preconditioned to the right temperature to ensure they bond properly with the chocolate. The chocolate itself is made from cocoa mass, cocoa butter, sugar, and milk solids, refined to a very fine particle size and conched to develop flavor and smoothness. It is then tempered, which means it is cycled through heating and cooling phases so that the cocoa butter crystallizes in a stable form. Proper tempering is crucial. It gives the chocolate its glossy appearance, prevents blooming, and ensures that satisfying snap. The enrobing machine works by creating a flowing curtain of tempered chocolate. The wafer fingers travel on wire mesh conveyors under this curtain, which coats them evenly on all sides. Excess chocolate drips away, and vibrating plates help smooth the coating and knock off any lingering drips. Air knives may be used to blow away excess chocolate, leaving a uniform finish. At this point, the bars have their characteristic shape, though they are still soft and need to be set. The freshly enrobed KitKat bars then move into long, cooling tunnels. These are climate-controlled chambers, often dozens of meters long, with carefully regulated cold air circulating to gradually solidify the chocolate. If the cooling is too fast, the chocolate can crack. If too slow, the bars may not set properly. Within these tunnels, the bars harden into the perfectly firm state that will hold through wrapping and storage. By the time they emerge, they are solid, glossy, and identical in size and shape. Packaging is the next critical step. KitKat packaging has evolved over the decades, but is always instantly recognizable with its bold red color and logo. In the factory, high-speed flow wrapping machines handle this stage. Printed rolls of film feed into the machines, where mechanical arms wrap the film tightly around each bar. Heat-sealing jaws close the ends, creating airtight seals that protect the product from moisture and contamination. Depending on the market, the bars may be wrapped individually, in multi-packs, or in sharing-size pouches. Packaging machinery works at breathtaking speeds, capable of wrapping hundreds of KitKats every minute, and sensors ensure that every wrapper is aligned so logos and text appear neatly. Quality control is woven into every part of the process. Technicians monitor wafer thickness, cream distribution, chocolate viscosity, and even the alignment of fingers within a bar. Automated vision systems scan products on the line, identifying defects such as cracks, uneven coatings, or misaligned wrappers. Bars that do not meet standards are diverted away from packaging, and often their components are recycled back into cream filling. Metal detectors and X-ray machines add another layer of safety, ensuring that no foreign particles end up in the final product. After packaging, finished bars are boxed and palletized automatically by robotic arms. These pallets are shrink-wrapped for stability and stored in climate-controlled warehouses until they are shipped out. Chocolate is extremely sensitive to heat and humidity, so maintaining proper conditions during storage and distribution is crucial. Logistics systems track inventory precisely, ensuring that KitKat bars reach retail outlets worldwide with freshness intact. The story of KitKat is also a story of history and branding. First created in the 1930s in England, it was marketed as a snack-sized chocolate bar that could be eaten during a work break. Over time, the famous advertising slogan encouraged consumers to have a break, have a KitKat, cementing its place as a snack associated with pause and relaxation. Today, KitKat is produced in multiple countries, with variations in flavor and size to suit regional tastes. But the core manufacturing process remains consistent across factories. The design of the KitKat is deceptively simple, but requires enormous precision. The clean snap of the chocolate coating, the crisp bite of the wafer, and the way the fingers break apart so neatly are all engineered results of carefully controlled baking, cutting, layering, enrobing, and cooling. Each finger has to line up perfectly. Each coating must be of consistent thickness, and each wafer must remain crisp inside its chocolate shell. Small deviations can ruin the experience, so factories invest heavily in automation, robotics, and quality assurance to maintain their standards. Technological advances continue to shape the production of KitKat. Energy-efficient ovens, improved tempering systems, and recyclable packaging films are increasingly being adopted. In some markets, factories are experimenting with reduced sugar or plant-based chocolate alternatives, reflecting consumer demand for healthier options. Despite these changes, the essence of KitKat remains unchanged. A satisfying combination of crisp wafer and smooth chocolate presented in its familiar breakable format. The journey begins with the chocolate itself, the heart of every M&M. The chocolate recipe varies slightly depending on whether the factory is producing classic milk chocolate, M&Ms, peanut-filled varieties, or other flavors, but the base always starts with cocoa mass, cocoa butter, sugar, and milk solids. These ingredients arrive at the factory in bulk form. Sugar is delivered in massive tankers and stored in silos, while cocoa products are shipped in blocks or liquid tanks, depending on the form. The chocolate-making process involves blending these ingredients in carefully measured proportions, then refining them into a smooth paste. Industrial refiners reduce particle size down to less than 20 microns, creating the silky mouthfeel consumers expect. The chocolate mass then undergoes conching, a prolonged mixing and heating step that develops the flavor by driving off acidity and moisture. Finally, the chocolate is tempered, a precise sequence of heating and cooling that ensures the cocoa butter forms stable crystals. Without tempering, the chocolate would appear dull, melt too easily, and develop white streaks known as bloom. Once the chocolate is ready, it is shaped into the small, lentil-sized centers that form the core of M&Ms. In the case of plain M&Ms, the chocolate is deposited into molds or extruded into droplets on cooling belts. The droplets solidify into small, round discs, uniform in size and weight. For peanut M&Ms, the process begins with sorting and roasting peanuts. Only peanuts of specific size and shape are used because uniformity is crucial to ensure that the sugar shell later adheres evenly. Each peanut is coated with a thin layer of chocolate by tumoring them in revolving pans where liquid chocolate is drizzled and solidified in successive layers. Over time, the peanut becomes encased in a smooth chocolate sphere, ready for sugar coating. The sugar shell, which gives M&Ms their iconic crunch and prevents the chocolate from melting in your hand, is applied through a process called panning. Panning is one of the oldest candy-making techniques, but modern M&M factories use highly advanced, automated versions of it. In these systems, thousands of chocolate centers are placed into large rotating drums. As the drums spin, a liquid sugar syrup is sprayed onto the tumbling centers. Each spray coats the candies lightly, after which warm, dry air is blown into the drum to evaporate moisture and harden the sugar. This process is repeated over and over, gradually building up the hard shell layer by layer. The result is a perfectly smooth, crunchy coating that encapsulates the chocolate completely. The next step is coloring, and this is where M&Ms become instantly recognizable. Once the sugar shell has been built up to the desired thickness, colored solutions are applied to the tumbling candies in the same panning drums. Food-grade dyes are mixed with sugar syrups and sprayed in measured amounts, creating vibrant red, yellow, green, blue, orange, or brown coatings. As before, the candies are dried with controlled air, and the process is repeated until each M&M has a consistent glossy color. Achieving even coverage is a challenge because each candy must look uniform despite being made in enormous batches. The panning drums, air temperature, spray nozzles, and syrup viscosity are all precisely controlled by computerized systems. At this stage, the candies already look like M&Ms, but they still lack the final detail, the iconic white letter M printed on each piece. Printing is performed using offset printing technology adapted for candy. The coated M&Ms pass through printing machines where edible white food coloring is transferred onto their surfaces using rubber plates engraved with the M design. As the candies move across the conveyors, rollers gently press the design onto each piece. This step may seem small, but it is surprisingly complex. The printing must be aligned properly, the color must adhere without smudging, and the process must be fast enough to keep up with the massive production speed of the line. Every piece is inspected visually or by optical sensors to ensure that the logo appears cleanly and consistently. Following printing, the M&Ms are polished to enhance their shine. Small amounts of edible waxes, such as carnauba wax or beeswax, are tumbled with the candies. This coating not only improves the gloss, but also provides additional protection against moisture and handling. After polishing, the candies are complete in terms of appearance and flavor, ready to be packaged. Packaging M&Ms is a highly automated operation involving sophisticated machinery. The candies are first weighed and portioned using multi-head weighers. These devices contain multiple weighing buckets that quickly dispense the exact quantity of M&Ms needed for each bag, tube, or pouch. The candies then drop into vertical form-fill seal machines, where printed rolls of film are shaped into bags, filled with candy, and sealed with heat. For larger formats, such as resealable pouches or plastic containers, the candies are dispensed into preformed packaging and sealed accordingly. High-speed packaging lines can produce thousands of units per hour, and advanced vision systems ensure that every package is filled accurately and sealed tightly. Throughout the entire production line, quality control is rigorous. Chocolate particle size is measured during refining, sugar coating thickness is monitored during panning, and color distribution is checked with optical sensors. Random samples are tested for taste, texture, and breakage resistance. Metal detectors and X-ray scanners ensure that no foreign particles contaminate the candy stream. Even the printing of the M is evaluated to maintain brand consistency. Defective candies are automatically rejected and sometimes recycled into other uses, such as being ground into fillings. Once packaged, pallets of M&Ms are wrapped and stored in climate-controlled warehouses. Chocolate candies are highly sensitive to heat and humidity, so maintaining stable conditions during storage and transportation is essential. Refrigerated trucks often move the products to distribution centers, from where they are sent to supermarkets, vending machines, movie theaters, and countless other outlets around the world. The M&M, first introduced in the early 1940s, was originally developed as a way to provide soldiers with chocolate that would not melt easily in hot climates. The sugar shell was the innovation that solved this problem, and it remains central to the candy's identity today. Over the decades, the product line has expanded to include peanut, almond, crispy, caramel, and many other varieties, each requiring slight adjustments to the core production process. Yet the essence remains unchanged. Chocolate at the center, a crisp sugar shell outside, vibrant colors, and the famous white M that sets it apart. The engineering behind M&Ms demonstrates how modern factories combine tradition with cutting-edge automation. Panning, a technique that dates back centuries, is scaled up to handle millions of candies at once. Printing, normally reserved for paper and packaging, is adapted to mark tiny edible surfaces with precision. Packaging machines work at breathtaking speeds while still maintaining accuracy to the gram. Every element of the process reflects both efficiency and attention to detail, qualities necessary to meet the massive global demand for these small candies. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit. and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final checkweigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers, and the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. The process for Reese's peanut butter cups begins with the sourcing of high-quality raw peanuts, which form the core of the filling. These peanuts are typically sourced from farms in the southeastern United States, particularly Georgia, Alabama, and the Carolinas, where the climate and soil are ideal for peanut cultivation. Once harvested, the peanuts undergo initial cleaning, shelling, and sorting at the agricultural level before being shipped in bulk to the Reese's production facility. Quality control teams inspect every shipment, screening for mold, aflatoxins, and other contaminants. Peanuts are often tested for size, moisture content, and oil composition to ensure batch consistency. Upon arrival at the factory, the peanuts are conveyed to large storage silos. From here, the process of transforming raw peanuts into the signature Reese's filling begins. The peanuts are first roasted in large-scale industrial roasters, long horizontal drums heated by indirect gas-fired flames. These rotating drums tumble the peanuts slowly, ensuring even roasting. Temperature and humidity are closely monitored throughout the roast cycle, typically maintained around 320 degrees Celsius for about 30 to 40 minutes, depending on the peanut variety and moisture content. Once roasted, the peanuts are quickly cooled using forced air cooling tunnels to halt further cooking. The skins are then removed using a process known as blanching. In mechanical blanches, peanuts are agitated against rough surfaces or rubber belts that strip away the thin, papery skins. A series of air jets and vibrating sieves separate the skins from the now blanched nuts. At this point, the peanuts are ready to be ground. In most candy factories, this process takes place in two distinct phases. First, a coarse grind reduces the peanuts into a crumbly paste. Then, a finer grinding process, often using high-speed colloid mills or stone rollers, produces a smoother texture. However, unlike creamy commercial peanut butters designed for spreads, Reese's peanut butter filling maintains a slightly gritty texture on purpose. This signature mouthfeel is the result of limiting the duration of the fine grind and carefully controlling moisture levels. The ground peanuts are blended with additional ingredients, including sugar, dextrose, salt, hydrogenated vegetable oils, and sometimes a small amount of molasses or corn syrup solids. This mixture is prepared in large industrial mixing tanks equipped with powerful paddle agitators that ensure even incorporation. The blending process is closely monitored for temperature, viscosity, and particle size distribution, which directly affect the final texture and handling characteristics. The resulting peanut butter filling is slightly crumbly, yet cohesive, designed to hold its shape when formed, but melt smoothly in the mouth. While the peanut butter filling is being prepared, another part of the factory is busy tempering chocolate. Reese's peanut butter cups use a custom milk chocolate formulation that includes cocoa solids, cocoa butter, milk fat, sugar, lecithin, and vanillin. These ingredients are pre-blended and then passed through conching machines, large vats where granite rollers continuously knead the chocolate for hours at elevated temperatures. Conching improves texture and flavor by breaking down particles and promoting the development of complex chocolate notes. After conching, the chocolate is sent to tempering units, which precisely heat and cool the chocolate in a controlled sequence to encourage the formation of stable cocoa butter crystals. Proper tempering is critical to achieving that characteristic Reese's snap and glossy finish. The chocolate must be maintained at a working temperature of approximately 88 degrees to 90 degrees for milk chocolate, depending on the formulation. Now the production line shifts into high gear with the molding and filling of each peanut butter cup. The factory floor features a long assembly line comprising conveyor belts, servo-driven depositing heads, forming stations, and robotic arms, all synchronized with computer-controlled systems. First, paper cup liners are dispensed from reels and dropped into aluminum or plastic molds that give the peanut butter cup its distinctive ridged edge. These molds are carried forward on the conveyor to the chocolate depositing station. Here, a metered amount of tempered chocolate is deposited into each mold cavity, typically via piston-driven depositors with highly accurate flow control. The molds are then gently vibrated to level the chocolate and remove any trapped air bubbles. A specialized spinning or centrifugal molding mechanism is often used to coat the sides of each liner with chocolate, forming a thin shell that will encase the peanut butter filling. Once the bottom and sides of the shell are set, often using brief passes through cooling tunnels chilled to 40 degrees F, the molds move to the filling station. At this point, the peanut butter mixture is slightly warmed to improve flowability and deposited into the center of the chocolate shell using a second set of depositors. The volume and placement are tightly controlled to ensure the filling does not breach the shell's perimeter, which would compromise product appearance and shelf life. The partially filled molds then travel through another cooling tunnel to partially firm up the filling before the final chocolate cap is added. At the next station, another measured deposit of tempered chocolate is layered on top to fully enclose the peanut butter. Vibratory and centrifugal actions again ensure that the top layer is smooth and fully seals the filling inside. After the top layer is applied, the molds pass through the final cooling tunnel. This tunnel, often more than 30 feet long, gradually lowers the product temperature to about 50 degrees to 60 degrees Fahrenheit, allowing the chocolate to fully crystallize and harden without cracking or bloom. At the end of the tunnel, robotic demolders invert the trays and the solidified Reese's peanut butter cups drop gently onto another conveyor belt, which carries them to the packaging line. Packaging is a critical part of the operation, both for aesthetics and product protection. Individual cups are wrapped in printed foil or plastic film using high-speed flow wrapping machines. These machines align, wrap, heat seal, and cut the packaging material in a continuous motion at speeds of hundreds of units per minute. Sensors and vision systems verify proper alignment, seal integrity, and date coding. Multiple wrapped cups are then grouped into standard pack formats, such as 2-packs, king size, or multi-packs, using pick-and-place robots that transfer the wrapped candies into cardboard sleeves or blister packs. These are then loaded into shipping cartons by automated case packers and sent through weight check stations and metal detectors for final safety assurance. Cartons are sealed, barcoded, and palletized using robotic palletizers that arrange the boxes into stable stacks ready for shipment. The finished pallets are shrink-wrapped for transport and loaded onto refrigerated trucks, if necessary, depending on the season and destination. Distribution centers receive the pallets and coordinate the movement of Reese's products to retail chains, vending machine operators, and wholesale clubs. Shelf life is generally around 6 to 9 months, and climate-controlled storage is crucial to preventing fat bloom or flavor degradation in the chocolate. Inventory is rotated using first-in, first-out logistics to ensure product freshness. Reese's peanut butter cups may seem like a simple treat, but their production involves a complex interplay of food science, automation, engineering, and quality control. Each cup reflects countless micro-adjustments made by operators, engineers, and sensors throughout the line to maintain consistency in taste, texture, and visual appeal. Whether you're biting into a miniature, a king size, or a seasonal shape, the same rigorous standards apply across every variation. The process for Snickers begins long before a single bar is formed. It starts with the procurement of raw ingredients, each of which must meet stringent quality, flavor, and food safety standards. The peanuts used in Snickers are typically sourced from large-scale growers in the United States, particularly Georgia, Texas, and Alabama, where soil composition and climate are well suited to peanut cultivation. Once harvested, the peanuts undergo shelling, drying, and initial quality control before arriving at the candy factory in bulk loads. At the receiving dock, they're sampled and inspected for size uniformity, absence of mold or aflatoxins, and overall freshness. The peanuts are then conveyed to roasting units, large, gas-fired, rotary drum roasters that tumble and cook the nuts evenly. Roasting time and temperature are carefully controlled, often in the range of 300 degrees to 330 degrees, to ensure the development of the characteristic deep nutty flavor and golden color. As the peanuts cool on vibratory trays with forced air, their skins are loosened and removed through mechanical blanching, which typically involves abrasion and suction systems. Once the peanuts are blanched, they are screened again for foreign matter or off-grade pieces before being held in stainless steel hoppers, ready for integration into the bar. While the peanuts are being prepared, another production stream begins with the making of the nougat layer, the foundational component of every Snickers bar. Nougat is a whipped mixture, typically composed of sugar, corn syrup, egg whites, and milk powder. The sugar and corn syrup are first combined in massive stainless steel cooking kettles, where they are heated to a precise temperature, usually around 240 degrees to 250 degrees, to achieve the correct sugar structure and viscosity. This hot syrup is then transferred to continuous mixing tanks, where it is combined with whipped egg whites and other dry ingredients. The blending process is highly aerated, giving the nougat its light, spongy texture. The finished nougat is deposited onto a moving conveyor belt lined with parchment or plastic film. It spreads out in a continuous sheet, generally about 1 to 2 inches thick. A series of levelers and rollers ensures uniform height and density across the sheet, which is then cooled slightly as it travels down the line. Once cooled and set, the nougat sheet proceeds to the caramel layering station. Caramel production occurs in its own dedicated section of the plant. A blend of glucose syrup, sucrose, dairy cream, and butter is cooked in open-jacketed kettles or vacuum cookers, where it is continuously stirred to avoid burning and to control the Maillard browning reactions that give caramel its signature flavor. The exact temperature and cooking duration are tightly monitored, typically between 240 degrees Celsius and 260 degrees. As soon as the desired consistency is achieved, firm enough to hold its shape but pliable enough to slice, it is poured or extruded onto the moving nougat sheet. The hot caramel forms a second, cohesive layer atop the nougat. To ensure perfect adhesion and uniform thickness, the bar sheet passes under heated rollers and through spreading nozzles that guide and adjust the caramel's distribution. The line is equipped with infrared sensors and weight check systems that continually monitor thickness and material ratios. Once the caramel has slightly cooled and stabilized, the bar sheet moves toward the peanut application zone. Roasted peanuts are sprinkled onto the warm caramel layer in a controlled shower using vibrating feed trays and metered dispensers. The combination of slightly sticky caramel and downward pressure ensures that most peanuts adhere securely. Excess or misaligned nuts are brushed away by rotating silicone paddles and collected for reuse or reprocessing. The peanuts used here are not only flavor critical, but also provide a distinctive crunch and texture contrast to the softer nougat and caramel. With all three internal layers assembled, nougat, caramel, and peanuts, The composite sheet now travels to the cutting area. Here, guillotine-style knives or rotary blade systems cut the long sheet into bar-length strips, typically around 1 inch wide. These strips are then cross-cut into individual bars using synchronized high-speed blades. Every bar is now a complete unit, except for the chocolate coating. Before coating, the uncoated bars, often referred to as centers, pass through a quick, chilling tunnel to firm up the layers and maintain bar integrity during enrobing. Once firm, the centers are deposited onto a wide enrobing belt that passes through a chocolate waterfall. This enrobing process involves a curtain of tempered milk chocolate cascading down over the moving bars. As the bars move through the curtain, chocolate coats the top and sides. A bottoming plate or chocolate pool beneath the bars coats the underside as well. The chocolate used in Snickers bars is a proprietary blend of milk chocolate ingredients: cocoa butter, cocoa liquor, sugar, milk solids, and emulsifiers. The chocolate is pre-tempered in dedicated machines that heat and cool it through specific curves to ensure stable crystal formation. This tempering is what gives Snickers its glossy finish and prevents fat bloom during storage. The temperature of the chocolate is carefully maintained between 86 degrees Celsius and 90 degrees Celsius throughout the enrobing line. As the chocolate-coated bars exit the enrober, they pass under air jets and vibrating rods known as air knives and vibrators that remove excess chocolate, improve coating uniformity, and give each bar its final shape. The still warm chocolate is soft and easily deformed, so the bars immediately enter a cooling tunnel, which gradually reduces their temperature to around 50 degrees Celsius in a staged fashion. This gradual cooling prevents cracking and ensures that the chocolate shell sets with the correct texture. Once fully cooled, the bars emerge, ready for wrapping. A high-speed automated packaging line awaits, where each bar is individually wrapped using roll-fed film wrappers. These machines synchronize bar movement with film feeding, folding, sealing, and cutting, all in one continuous operation. Heat sealers close the film edges with precision, while inline printers apply best buy dates, lot numbers, and traceability codes. The wrapped bars are then conveyed to a grouping station. Depending on the market, Snickers bars may be packed individually, bundled in twin packs, or combined into multi-unit boxes. Robotic arms sort and orient the wrapped bars, placing them into cartons that are then sealed with hot melt adhesive. The packed cartons are passed through metal detectors and weight verifiers as a final check before palletization. Palletizing robots load the boxes onto standardized pallets, wrapping them tightly in plastic film for protection and stability during shipping. From there, pallets are staged in climate-controlled distribution centers. Temperature and humidity must be carefully controlled, especially in warm climates, to preserve the bar's texture and chocolate integrity. Snickers bars are then distributed to retailers, wholesalers, and vending machine operators worldwide. Shelf life for a standard Snickers bar is generally between 9 and 12 months, assuming proper storage. Mars maintains rigorous quality control protocols, including sampling every batch for flavor consistency, structural integrity, and microbiological safety. Automated inspection systems use vision technology to detect misaligned bars, incomplete coatings, or wrapper defects, automatically removing flawed units from the line. Throughout the plant, hygiene is paramount, with clean-in-place systems for all equipment and strict allergen controls to ensure product safety. What makes Snickers particularly remarkable is how such a complex, multi-layered treat can be produced with such uniformity at an industrial scale. From raw peanuts and liquid caramel to perfectly wrapped bars stacked on pallets, every aspect of production is optimized for speed, precision, and global distribution. Millions of Snickers bars roll off the line each day, each one representing a perfected system of mass food manufacturing. It all begins with cocoa beans for Hershey's chocolate, which are the fundamental raw ingredient in all chocolate. Hershey sources its cocoa beans primarily from West Africa, countries like Côte d'Ivoire and Ghana, where the climate, soil, and traditional farming practices produce high-yield crops with desirable flavor characteristics. Once harvested, the cocoa beans are fermented in banana leaf-lined piles and dried under the sun before being packed in jute bags and shipped across the ocean to Hershey's production facilities in the United States. Upon arrival, the beans are subject to rigorous testing. Random samples from each shipment are roasted and analyzed for aroma, acidity, moisture content, and potential contaminants. Approved beans are stored in large silos, sorted by origin and quality grade. From here, the first major step in the chocolate making process begins roasting. Roasting is not just about cooking the beans, it's a chemical transformation that unlocks the complex flavors hidden within the cocoa nibs. The beans are fed into large, rotating drum roasters or continuous belt roasters and exposed to carefully controlled dry heat at temperatures between 250 degrees and 300 degrees for 20 to 30 minutes. This Maillard reaction develops the chocolate flavor while drying the beans further and loosening the outer shells. The duration and temperature of the roast are adjusted depending on the origin and size of the beans, with constant airflow and humidity control. After roasting, the beans are cooled and sent through cracking machines that break them open, separating the brittle outer shells from the inner nibs. The broken shell pieces are removed through winnowing, a process that uses airflow to lift away the lighter shells, leaving behind clean cocoa nibs. These nibs are the essence of chocolate, rich in cocoa solids and cocoa butter. The nibs are then ground into a thick, gritty paste called chocolate liquor, not to be confused with alcohol. This step is performed in heavy-duty grinding mills, such as stone refiners or steel disc mills, which apply intense pressure and friction. As the nibs break down, their fat melts, turning the mass into a thick, flowing fluid. At this point, the chocolate liquor is still unrefined, with a coarse texture and bitter flavor. For milk chocolate, Hershey adds a blend of sugar, milk ingredients, and sometimes vanilla and lecithin to the chocolate liquor. One of the defining features of Hershey's milk chocolate is its use of fresh fluid milk that is processed in-house. Unlike European chocolates that often use powdered or condensed milk, Hershey pioneered a method of processing fresh milk into milk crumb, a dehydrated mixture of milk solids and sugar, using vacuum cooking and drum drying techniques. This milk crumb, with its slightly tangy cooked flavor, contributes to the uniquely Hershey taste. The chocolate liquor, milk crumb, and sugar are blended in large stainless steel mixing tanks, forming a uniform paste. At this stage, the mixture is still coarse and gritty, unsuitable for final chocolate texture. It must be refined. The refining process involves passing the chocolate mass through a series of roller mills, typically 5-roll refiners that reduce the particle size of the solids to less than 30 microns. The goal is to achieve a silky smooth mouthfeel without any noticeable graininess. Once refined, the chocolate enters the conching phase, one of the most critical steps in flavor development. Conching is a process of continuous mixing, aerating, and heating the chocolate over many hours to improve its taste and texture. Hershey's uses a combination of traditional longitudinal conches and modern rotary conches that knead the chocolate at controlled temperatures, typically between 120 degrees and 180 degrees. This process helps evaporate undesirable volatile acids, mellow bitter notes, and fully integrate the milk and cocoa flavors. The viscosity and aroma are fine-tuned during this stage through mechanical shearing and time adjustments. Following conching, the chocolate undergoes tempering, a heat treatment process that ensures the final product has a smooth, glossy finish and a crisp snap when broken. Cocoa butter can crystallize in several forms, but only one, known as Form 5, gives chocolate its ideal physical properties. Tempering involves heating the chocolate to about 115 degrees, then cooling it down to around 80 degrees, and finally reheating it slightly to about 88 degrees to promote the formation of stable crystals. This carefully controlled cycle is performed in continuous tempering machines, which maintain consistent temperatures and flow rates. Tempered chocolate is now ready for molding. Hershey's uses high-speed molding lines where liquid chocolate is deposited into polycarbonate molds in precise weights. The molds are vibrated to remove air bubbles and ensure even distribution. For classic bars like the Hershey's Milk Chocolate Bar, the molds are designed with the familiar rectangular break-apart sections embossed with the Hershey name. Once filled, the molds travel through long refrigerated cooling tunnels where the chocolate solidifies into its final form. As the bars cool, They are monitored by temperature sensors and mechanical feelers to ensure proper release. When fully set, the bars are automatically ejected from the molds and conveyed to the wrapping station. Modern wrapping equipment is synchronized with bar output and uses roll-fed film that is printed with the Hershey's branding, ingredients, and expiration codes. Wrappers are folded and sealed using rotary crimpers, and a barcode is applied for tracking. Wrapped bars are then grouped into cartons or display trays using robotic pick-and-place systems and conveyed to the end-of-line packaging area. Here, cases are formed, filled, and sealed before being palletized by automated arms. Each pallet is shrink-wrapped and scanned into inventory, ready for transport to distribution centers across the country and around the world. Throughout the entire process, quality control is a constant presence. Samples are pulled from every batch for testing. Sensory panels evaluate flavor and aroma, while lab technicians measure moisture content, fat percentage, and microbial levels. Machine vision systems inspect each bar for dimensional accuracy and surface defects. Metal detectors and X-ray machines scan for foreign objects, while thermal imaging cameras check for temperature compliance at various stages. Behind the scenes, Hershey's factories are tightly integrated with computerized control systems that track every ingredient, process parameter, and output metric in real time. From ingredient blending to chocolate tempering and bar wrapping, programmable logic controllers and supervisory control and data acquisition systems coordinate the hundreds of motors, valves, conveyors, and sensors that make up the line. These systems not only maximize efficiency and reduce downtime, but also ensure that each bar tastes the same as the one before it. Once packaged and palletized, Hershey's bars enter the post-production logistics chain. Distribution centers maintain climate-controlled storage to preserve chocolate integrity. Trucks are loaded according to first-in, first-out scheduling, and GPS tracking systems ensure timely delivery to retailers, vending machine operators, and wholesalers. Chocolate bars are especially sensitive to heat and humidity, so strict environmental controls are observed throughout transportation and warehousing to prevent melting or bloom. Interestingly, the Hershey flavor that many Americans recognize and even associate with nostalgia is not accidental. It's the result of deliberate formulation choices, particularly in how milk is treated during production. Some analysts believe the signature, slightly sour or tangy flavor found in Hershey's milk chocolate comes from the breakdown of milk fats into butyric acid during controlled lipolysis, an effect that differentiates Hershey's from creamier European chocolates. This flavor profile has become a cultural benchmark in the United States, deeply woven into American food identity. Despite decades of innovation and scaling up, the heart of Hershey's chocolate production still echoes the vision of its founder: to make high-quality milk chocolate affordable and accessible to everyone. With more than a century of history and tens of millions of bars produced annually, Hershey's remains a pioneer in automated food manufacturing, exemplifying the blend of tradition, precision engineering, and industrial food science. From bean to bar, the production of Hershey's chocolate is a story of transformation, driven by technology, but grounded in flavor. Nutella's key ingredients are hazelnuts, sugar, palm oil, cocoa solids, skimmed milk powder, whey powder, lecithin as an emulsifier, and vanillin as a flavoring agent. Each of these ingredients is sourced globally, selected for consistency, taste, and availability. Hazelnuts, the signature ingredient, are predominantly sourced from Turkey, which produces more than 2/3 of the world's supply. However, Italy, Chile, and the United States also contribute to the global hazelnut harvest. Ferrero, the company behind Nutella, maintains long-term relationships with growers and has implemented traceability programs to ensure that hazelnuts meet quality standards for moisture content, size, and taste. Upon arrival at the processing facility, hazelnuts go through rigorous inspection and sorting procedures. This is a critical control point because the quality of the nut directly affects the flavor and texture of the final product. Optical sorters and vibrating sieves are used to remove debris, stones, and underdeveloped nuts. The selected hazelnuts are then subjected to a deshelling operation using mechanical crushers that crack the shells without damaging the kernels. These kernels are further inspected and cleaned before being sent to large-scale roasting units. Roasting is one of the most important flavor development stages in Nutella production. In industrial operations, continuous roasting ovens are used, where hazelnuts travel through a rotating drum or along a conveyor belt under a flow of hot air, typically between 140 to 160 degrees Celsius. Roasting duration and temperature are carefully controlled to bring out the nutty aroma and to reduce moisture to below 5%. After roasting, the nuts are cooled quickly to preserve their volatile aromatic compounds and prevent overcooking. The cooled hazelnuts are then transferred to grinding machines, where they are ground into a paste using roller mills and high-speed grinders. The result is a fine hazelnut paste with a smooth texture ready to be incorporated into the final mix. Meanwhile, other key ingredients are prepared in parallel. Sugar, which makes up a significant portion of the spread, is delivered in bulk as granulated white sugar. Before use, the sugar is pulverized in industrial fine grinders or pin mills until it becomes a powdered form with consistent particle size, often below 30 microns, to avoid any grittiness in the final texture. This powdered sugar is stored in silos and fed into the mixing tanks using pneumatic conveying systems. Cocoa solids, another essential ingredient, are typically received as cocoa powder. This powder undergoes sifting and magnetic separation to remove any foreign particles or metallic fragments. Skimmed milk powder and whey powder, both derived from dairy processing, are reconstituted into a slurry with water or added in dry form depending on the plant design. These milk-based ingredients contribute not only to flavor, but also to the creamy mouthfeel and protein content of the spread. Palm oil is selected for its semi-solid consistency at room temperature, which is ideal for producing a spreadable product that does not require refrigeration. Before blending, palm oil is filtered and heated to a controlled temperature to ensure uniform mixing. It is pumped into heated storage tanks, where it is kept in liquid form and circulated to prevent crystallization. Once all base ingredients are prepared, the process of mixing begins in large-scale stainless steel mixing tanks. These tanks are fitted with high-torque agitators and precision load cells that measure the exact quantity of each ingredient added. The powdered sugar, hazelnut paste, cocoa powder, milk powder, and palm oil are introduced sequentially, followed by small quantities of lecithin and vanillin. Lecithin acts as an emulsifier, allowing the fat-based palm oil to bind with the water-based milk components, ensuring the product remains stable and homogeneous. Vanillin, a synthetic or natural flavoring, gives Nutella its distinct sweet aroma. The mixture is subjected to a refining process to achieve the desired texture and particle size. This is often accomplished using 5-roll refiners or conching machines. The 5-roll refiner uses a series of precision-engineered steel rollers that progressively grind the mixture to a fine, uniform consistency, typically achieving particle sizes of around 20 microns. This stage is crucial for eliminating any detectable graininess, resulting in the smooth, velvety texture Nutella is known for. In some facilities, a conching step follows refining. In conching, the mixture is kneaded and aerated for several hours in large heated vessels. The process further develops flavor, reduces acidity, and allows volatile off flavors to evaporate. Temperature, shear force, and mixing speed are all tightly controlled to maintain product consistency. After conching, the mixture is cooled slowly to prevent separation and to stabilize the emulsion. Once the spread reaches the correct viscosity and temperature, it is pumped through sanitary pipelines to the filling stations. Filling lines are fully automated and consist of synchronized conveyor systems, rotary fillers, and capping machines. The jars, made from glass or plastic, are cleaned with compressed air or ionized air blowers before being filled. Filling heads dispense the exact amount of Nutella into each jar with remarkable precision, ensuring minimal variation between units. Immediately after filling, jars pass through a sealing station where a foil membrane is applied to the mouth of the jar. This step is critical for maintaining freshness and preventing microbial contamination. The foil seal is typically induction sealed using a non-contact electromagnetic process that heats the foil and causes it to bond to the jar rim. Once sealed, the jars are capped with tamper-evident lids and conveyed to labeling machines. High-speed labelers apply brand-specific labels with information such as batch number, expiration date, and ingredients. Each jar then proceeds through a series of quality control checkpoints. These include weight checks, vision systems to verify correct sealing and labeling, and metal detection to ensure product safety. Defective units are automatically rejected and diverted for reprocessing or disposal. The entire packaging area is designed with hygiene in mind, using positive air pressure zones, clean-in-place systems, and stainless steel surfaces to reduce contamination risk. After packaging, Nutella jars are grouped into cartons or shrink-wrapped multi-packs, then stacked on pallets using robotic arms. Pallets are stretch-wrapped and labeled with barcodes for inventory tracking. From here, the product enters the distribution phase. Nutella's distribution logistics are a finely tuned operation. Pallets are stored temporarily in climate-controlled warehouses where temperature and humidity are maintained to prevent oil separation or spoilage. Inventory management systems track product movement using real-time data. Distribution centers coordinate with retailers, wholesalers, and export logistics to move products efficiently. Nutella is shipped in refrigerated or insulated containers only when necessary, though its high fat, low moisture content gives it considerable shelf stability. Throughout its supply chain, Nutella maintains compliance with international food safety standards such as ISO 22000, BRC, and HACCP protocols. Auditors regularly inspect facilities for compliance, and the entire process from hazelnut sourcing to jar sealing is documented for traceability and recall readiness. Automation, data collection, and machine learning are increasingly used to optimize processes, predict maintenance needs, and reduce waste. What makes Nutella's production so compelling is the precise synchronization of global sourcing, advanced food engineering, and automation technologies that allow for the consistent output of millions of jars per day. Every batch is a result of not just culinary science, but also the collaboration of agronomists, engineers, food technologists, and supply chain experts. Beyond the factory floor, Nutella's evolution continues with reformulations aimed at reducing sugar or incorporating more sustainable palm oil. Efforts to use recyclable packaging and implement blockchain for ingredient tracking reflect broader industry trends towards transparency and environmental responsibility. The foundation of Jif begins with its primary ingredient, peanuts. Specifically, the variety used in commercial peanut butter production is often the runner peanut, prized for its uniform kernel size, mild flavor, and high oil content. These peanuts are primarily grown in the southeastern United States, including states like Georgia, Alabama, and Florida, where sandy soils and warm climates create optimal growing conditions. Jif, owned by the J.M. Smucker Company, works closely with peanut growers through long-standing contracts to ensure consistent quality and supply. Before the peanuts even reach the factory, they're subjected to extensive grading systems operated by the USDA, evaluating factors like kernel size, moisture content, and damage from mold or pests. Once harvested, the raw peanuts are cured by drying them to a safe moisture level, usually around 10%. This drying stage is essential to prevent mold growth during transport. The peanuts are then shelled using mechanical shellers that crack the outer holes while leaving the kernels intact. After shelling, the peanuts are cleaned using air classifiers and vibrating screens to remove debris, dirt, and remaining shell fragments. These cleaned kernels are then transported in bulk to Jif's dedicated peanut butter production facilities, where their transformation truly begins. Upon arrival at the factory, peanuts undergo a second round of cleaning and quality control. Optical sorters equipped with high-speed cameras and sensors scan each peanut at astonishing rates, removing any discolored, damaged, or foreign material contaminated nuts. Metal detectors are also employed at this stage to ensure there are no traces of metal debris from harvesting equipment. These steps are critical not only for food safety, but also for maintaining Jif's smooth and consistent flavor. The next stage is roasting, arguably the most important phase for flavor development. Industrial peanut roasters are highly sophisticated machines capable of handling thousands of pounds of peanuts per hour. Jif uses a continuous dry roasting process where peanuts are evenly fed onto a perforated conveyor belt that moves through a tunnel of hot, forced air. Temperatures during roasting typically range between 160 and 180 degrees Celsius, with exact values finely tuned based on peanut size, oil content, and desired flavor profile. This process typically takes 15 to 30 minutes and is closely monitored using infrared sensors and real-time moisture analyzers. As peanuts roast, their proteins and sugars undergo Maillard browning, creating hundreds of volatile aroma compounds that contribute to peanut butter's distinctive roasted flavor. Immediately after roasting, the peanuts are rapidly cooled using chilled air blowers to stop the cooking process and lock in the developed flavors. This cooling also prevents oil separation and oxidation, both of which can negatively impact product shelf life. At this point, the roasted peanuts are ready to be ground, but first they must be blanched. Blanching in peanut butter production refers not to cooking in water, but to the mechanical removal of the thin, papery red skins that surround the kernels. In Jif's facilities, peanuts are sent through dry blanchers, machines that tumble the nuts at high speeds while heated air loosens the skins. Rotating brushes then remove the skins entirely, and high-capacity vacuum systems suck away the debris. The blanched peanuts are now a light golden color and are inspected one final time before grinding. The grinding stage is where peanuts are turned into a thick, luscious paste. Jif's production lines use a two-stage grinding process to achieve the brand's famously smooth consistency. First, peanuts are coarse ground using heavy-duty industrial grinders. These machines use stainless steel burrs or hammer mills to crush the nuts into a semi-solid mass known as peanut paste. This paste still contains some coarse particles and has not yet achieved its final texture. Next, the coarse paste is fed into ultra-high-speed fine grinders, often colloid mills, which apply extreme shear forces to reduce particle size down to 10 to 15 microns. This is a crucial target, as particle size below 20 microns ensures a mouthfeel that is perceived as completely smooth by consumers. During this stage, other ingredients are also introduced into the mixture. These include sugar, fully hydrogenated vegetable oils, salt, and sometimes molasses, or mono and diglycerides. The oils, often made from rapeseed, cottonseed, or soybean, are used to stabilize the peanut butter and prevent oil separation on the shelf. Unlike palm oil or liquid vegetable oil, fully hydrogenated oils remain solid at room temperature and help give Jif its stable texture without requiring stirring. These additional ingredients are metered in with extraordinary precision using automated dosing systems connected to load cells and flow meters. Inline mixers ensure that each component is fully dispersed throughout the peanut paste. The temperature during grinding is carefully controlled, typically held between 60 and 75 degrees Celsius, to keep the product fluid without degrading flavor compounds. Once the peanut butter has been ground to the desired texture and all ingredients are thoroughly incorporated, it enters a holding tank under nitrogen blanketing. This protective gas layer prevents oxidation and helps preserve freshness during the short holding period before packaging. The product is then pumped to the filling lines through a network of heated sanitary stainless steel piping. Jif's packaging lines are models of efficiency and automation. Plastic jars, blow molded from PET or HDPE, are automatically unscrambled and conveyed into position. Before filling, jars pass through an air rinse station that uses ionized air to remove dust or plastic fragments. High-speed rotary piston fillers dispense precise volumes of peanut butter into each jar, minimizing air entrapment to avoid spoilage and maintain shelf life. Filled jars are then capped immediately using torque-controlled capping heads that screw on tamper-evident lids. After capping, jars pass through induction sealers where a foil membrane is bonded to the jar rim. This step uses electromagnetic energy to heat and seal the foil in milliseconds, creating a hermetic barrier that locks in flavor and protects against microbial contamination. The sealed jars move to labeling machines, where front and back labels are applied, followed by laser or inkjet printers that mark each jar with batch codes, production dates, and plant IDs. Throughout this packaging process, quality control is constant and rigorous. Automated vision systems inspect each jar for correct fill height, proper labeling, and cap placement. Metal detectors and X-ray scanners identify any contamination before product leaves the factory. Random samples are also pulled for texture analysis, oil separation testing, sensory panels, and microbiological screening. Any deviation from specifications leads to immediate corrective actions, and defective jars are removed from the line. Packaged jars are grouped into corrugated cardboard cases using robotic case packers. These cases are palletized by programmable robotic arms and stretch wrapped to ensure stability during transport. Each pallet receives a barcode label integrated into Jif's warehouse management system, allowing for real-time traceability from production to point of sale. Once palletized, the finished peanut butter is moved to distribution centers equipped with temperature and humidity control. Although Jif peanut butter is shelf-stable and does not require refrigeration, maintaining moderate temperatures during warehousing and shipping helps preserve flavor and prevent oil migration or texture degradation. From these central hubs, Jif is shipped to retailers, wholesalers, and export customers across the country and around the globe. The journey from raw peanut to finished jar is guided not only by mechanical precision, but also by a deep understanding of food chemistry, microbiology, logistics, and consumer expectations. Behind the familiar red-lidded jar is a network of engineers, food scientists, supply chain analysts, and production operators, all working in synchrony to ensure that every spoonful of Jif meets exacting standards. Advancements in automation and data analytics continue to refine the process. Modern Jif facilities are equipped with real-time monitoring systems, predictive maintenance software, and even machine learning algorithms that optimize roasting profiles based on moisture content and kernel density. Environmental controls ensure energy efficiency and waste reduction, and partnerships with peanut growers include sustainability initiatives aimed at soil conservation and water use reduction. The story of Hershey's syrup begins with its core ingredients: cocoa, sugar, water, corn syrup, salt, preservatives, and a few functional additives like potassium sorbate and xanthan gum. Each of these components is sourced with meticulous care to ensure consistency and food safety. Cocoa powder, the primary flavoring agent, is typically sourced from West Africa, where the Hershey Company partners with certified cooperatives to encourage sustainable farming practices. The cocoa beans are fermented, dried, and shipped to the US, where they are roasted, ground, and pressed into cocoa cake. This cake is then pulverized into a fine cocoa powder, standardized for fat content, flavor profile, and color intensity. Upon arrival at Hershey's syrup production facilities, All ingredients undergo rigorous testing. The cocoa powder is checked for microbiological safety, color consistency, particle size, and moisture levels. Sugar, often in granulated form, is tested for crystal uniformity, purity, and absence of foreign materials. Corn syrup, used as both a sweetener and thickener, is delivered in tanker trucks and stored in heated silos. It is continuously circulated to prevent crystallization or microbial growth. Water used in the process is treated on-site, filtered, softened, and sanitized using UV light or reverse osmosis to ensure purity and microbial control. The first major production stage is blending the dry and liquid ingredients. The process typically starts with the creation of a sugar corn syrup slurry. In large stainless steel jacketed mixing tanks, granulated sugar is combined with warm water and corn syrup under controlled agitation. These tanks are equipped with variable speed mixers and internal temperature sensors to maintain optimal dissolution rates. The heating jackets help bring the mixture to a consistent temperature, usually between 55 and 70 degrees Celsius, to accelerate solubility while avoiding caramelization. Once a uniform syrup base is achieved, cocoa powder is added. However, dry cocoa is notoriously difficult to hydrate due to its high fat content and fine particle size, which cause it to float and form lumps when introduced to liquid. To overcome this, Hershey's production lines utilize high shear mixers and vacuum-powered powder feeders. The vacuum system pulls cocoa powder directly into the liquid stream, minimizing clumping and ensuring uniform dispersion. Simultaneously, high-speed rotor-stator mixers or inline homogenizers shear the mixture at thousands of RPMs, breaking down any agglomerates and producing a velvety, uniform chocolate syrup base. At this stage, salt and preservatives such as potassium sorbate are also introduced. These additions are precisely dosed using automated ingredient hoppers that weigh each component before releasing it into the blanders. Potassium sorbate acts as a mold and yeast inhibitor, extending the product's shelf life. Some formulations may also include citric acid or sodium citrate to adjust pH, which affects both microbial stability and flavor brightness. The syrup then enters the cooking phase. Unlike batch cooking in traditional kitchens, industrial syrup production uses continuous flow heating systems. The chocolate slurry is pumped through tubular or plate heat exchangers, where it is heated rapidly to pasteurization temperatures, typically between 85 and 95 degrees Celsius. This thermal treatment destroys any remaining microbial contaminants and activates the emulsifiers and stabilizers added in earlier steps. The product is held at this temperature for a specific dwell time as it flows through holding tubes, ensuring regulatory compliance with pasteurization standards. After cooking, the syrup must be cooled quickly to prevent overcooking and maintain the desired viscosity and flavor. This is achieved using chilled water heat exchangers, which rapidly bring the syrup down to below 30 degrees Celsius. Rapid cooling also helps stabilize the emulsion, locking in the texture and preventing ingredient separation. The cooled syrup is then transferred to intermediate holding tanks, where it is gently agitated and blanketed with nitrogen gas to minimize oxidation. At this point, the syrup undergoes several quality control checks. Samples are pulled and tested for viscosity using rotational viscometers, ensuring that the pourability matches the brand's standard profile. Colorimeters assess chocolate intensity and hue, while refractometers measure sugar concentration. In parallel, sensory panels may be employed to evaluate flavor, mouthfeel, and aroma. Microbial testing is conducted on every batch to confirm that pasteurization was effective and that no contamination has occurred. Once the product passes quality control, it is sent through final filtration before packaging. Fine mesh inline filters remove any particulate matter that may have formed during cooking or cooling. This ensures a perfectly smooth syrup with no grit or undissolved solids. Packaging Hershey's syrup involves a highly synchronized series of steps designed for both hygiene and speed. The most common containers are squeezable plastic bottles, which are blow molded from PET or HDPE on site or delivered pre-formed. These bottles are first conveyed through an air rinse system that blasts ionized air to remove dust or debris. They are then indexed into position beneath the filling nozzles. Filling is performed using servo-controlled, volumetric, or piston fillers. These machines are calibrated to deliver exact quantities of syrup, typically in the range of 650 to 800 grams per bottle, depending on size. The syrup is dispensed at controlled speeds to prevent splashing or air entrapment. No drip filling heads are often used to maintain clean bottle exteriors and reduce product waste. After filling, the bottles move to the capping station. Caps are sorted using centrifugal feeders and applied using torque-monitored capping heads, which ensure a tight seal without over-tightening. Each bottle is then passed under an induction sealer, where an aluminum foil seal is bonded to the bottle mouth using electromagnetic heating. This tamper-evident seal not only enhances shelf life, but also guarantees product integrity. Next, the bottles pass through a labeling machine where pressure-sensitive labels are applied with exacting precision. Labels include not just branding and nutrition information, but also critical traceability codes, including batch numbers, timestamps, and plant identifiers. These details are laser etched or printed using inkjet coders. Before leaving the line, every bottle passes a series of automated inspection stations. Vision systems equipped with high-speed cameras check for correct fill levels, cap placement, seal integrity, and label alignment. Any non-conforming product is rejected and diverted to a separate inspection area for manual review. Approved bottles are grouped into cartons or shrink-wrapped multi-packs. Robotic case packers load the bottles into boxes, which are then sealed, labeled, and palletized. These pallets are stretch-wrapped and tagged with scannable barcodes for warehouse tracking. The entire process from filling to palletization is fully integrated into Hershey's manufacturing execution system, allowing for real-time monitoring and inventory control. Palletized syrup is transported to climate-controlled distribution centers. While Hershey's syrup is shelf-stable, temperature extremes can still impact viscosity and appearance. Warehouses maintain stable conditions to prevent thickening in cold weather or oil separation in high heat. From there, the product is dispatched to retail partners, online fulfillment centers, and export destinations. Throughout the supply chain, Hershey's implements strict food safety protocols, including compliance with the Global Food Safety Initiative, hazard analysis and critical control points, and FDA regulations. Traceability is maintained from raw cocoa bean to finished bottle, ensuring any issue can be traced and contained within hours. What makes Hershey's syrup so enduring in the marketplace isn't just its flavor, it's the precision and consistency made possible through modern food engineering. Every step of the process, from the aggressive mixing of cocoa powder to the final induction seal, is executed with scientific rigor. Equipment calibration, ingredient testing, and continuous improvement protocols ensure that each bottle tastes the same, pours the same, and satisfies the same cravings generation after generation. As the brand moves forward, sustainability is becoming an even greater focus. Efforts to reduce plastic use in packaging, improve energy efficiency in heating and cooling systems, and source more ethical cocoa are all part of Hershey's long-term production goals. Some lines are exploring bio-based PET alternatives for bottles and increasing recycling within plant operations. Continuous feedback from quality assurance teams and customer satisfaction metrics are used to refine processing parameters and optimize flavor retention across product shelf life. The journey begins long before the ice cream bar takes its recognizable shape. At the heart of Magnum's appeal is its dense, creamy ice cream base, typically made from a high butterfat dairy mix that gives it its rich mouthfeel. The base ingredients include whole milk, cream, sugar, glucose syrup, and sometimes egg yolk for additional texture. These raw materials are sourced from vetted dairy farms and suppliers that comply with stringent quality control measures. Upon arrival at the production facility, the dairy ingredients are immediately transferred into refrigerated holding tanks to maintain their integrity. Here, laboratory technicians perform routine tests for microbiological safety, fat content, and pH levels to ensure the base meets the strict specifications required for premium ice cream. Once the ingredients pass inspection, they're pumped into large stainless steel mixing tanks. These tanks are equipped with high-shear agitators that blend the milk, cream, and sugars into a homogeneous mix. During this phase, emulsifiers and stabilizers, such as mono and diglycerides or guar gum, are added to enhance the creaminess and improve the shelf life of the product. The mixture is continuously agitated and brought to a temperature of approximately 60-70 degrees Celsius to fully dissolve the sugars and emulsify the fats. The next critical step is pasteurization. The liquid mix is sent through a continuous flow pasteurizer, usually a plate heat exchanger, where it is rapidly heated to around 83 degrees Celsius for about 15 seconds. This high temperature, short-time pasteurization process ensures the destruction of harmful bacteria while preserving the functional properties of the dairy. Immediately after pasteurization, the mix is flash-cooled to below 4 degrees Celsius to minimize microbial growth and is transferred to maturation tanks. In the maturation tanks, which are jacketed vessels with slow-moving agitators, the mix is held at low temperatures for 4 to 12 hours. This resting period allows the emulsifiers and stabilizers to hydrate fully and the fat globules to partially crystallize. Maturation significantly improves the whipping quality of the mix and enhances the texture and body of the final ice cream. With the mix properly matured, it is now ready for freezing. The liquid base is pumped into continuous freezers, which are essentially refrigerated barrel drums equipped with rotating scraper blades. As the mix is pumped through these freezers, it is simultaneously aerated and frozen. The aeration, or overrun, is carefully controlled to maintain Magnum's signature dense texture, with overrun values kept well below standard commercial ice cream. The continuous freezer operates at sub-zero temperatures, rapidly freezing the mix to around -5 degrees Celsius while incorporating microbubbles of air for creaminess. At this semi-frozen stage, the ice cream has reached a soft serve consistency and is now ready for molding. One of the defining features of Magnum bars is their perfectly oval, bar-shaped form. This is achieved using a high-speed rotary molding system. Rows of stainless steel molds, pre-chilled to approximately -30 degrees Celsius, are arranged on a conveyor belt that dips them into a vat of liquid ice cream. As the molds emerge from the bath, the ice cream begins to freeze instantly against the chilled metal surfaces. To ensure a consistent core, the partially filled molds are passed through a hardening tunnel. This tunnel is essentially a blast freezer operating at -40 degrees Celsius or lower, using forced air circulation to rapidly solidify the product. Once hardened, the bars are extracted from the molds using a short burst of warm air or a mechanical press system. Immediately upon demolding, the ice cream bars are affixed to wooden sticks via a precise robotic inserter. These sticks, usually made of sustainably sourced birch or poplar wood, are sterilized and fed into the system through automated dispensers. Now comes one of the most iconic steps in the process: the chocolate enrobing. Magnum's chocolate coating is what sets it apart from most other ice cream bars. The chocolate used is often Belgian in origin and must meet exacting melt and viscosity specifications. It arrives at the factory in solid form and is melted down in jacketed tanks fitted with stirrers that maintain a constant, uniform temperature, typically around 40-45 degrees Celsius, to ensure a smooth flow. The hardened ice cream bars are conveyed toward the enrobing station, where they pass over a curtain of liquid chocolate. Each bar is dipped or showered with the molten coating using a carefully calibrated nozzle system. The chocolate immediately begins to solidify upon contact with the supercooled surface of the ice cream, forming the signature crack when bitten into. To achieve a uniform coating thickness, the enrobing line is equipped with vibration tables and air knives that remove excess chocolate without disturbing the integrity of the shell. Depending on the variant, classic, almond, white, or one of the many seasonal releases, additional toppings like almond pieces, cookie crumbles, or caramel swirls are applied to the wet chocolate shell before it fully sets. These inclusions are dispensed via gravimetric feeders or rotating drum applicators that ensure even distribution. Once enrobed and topped, the bars are transferred into a secondary hardening tunnel for final crystallization. This second blast freezer brings the core temperature of the bar down to around -18 degrees Celsius or lower, locking in the texture and ensuring long-term stability. After hardening, the bars move into the packaging area, a highly automated zone designed for speed and hygiene. Here, the products are first visually inspected, sometimes with the help of AI-based vision systems, to detect any surface defects, asymmetry, or misapplied toppings. Acceptable bars are funneled into flow wrapping machines that wrap each individual bar in a high barrier plastic film. This film is not just for branding and appeal, it plays a vital role in protecting the product from moisture migration, freezer burn, and flavor loss. Each wrapper is pre-printed with product information, including batch codes, manufacturing dates, allergen warnings, and nutritional data. A thermal transfer printer applies dynamic codes as the film passes through the wrapping head. After sealing, the bars are grouped in cartons, often using robotic arm sorters, and packed into corrugated boxes, ready for cold chain logistics. Throughout the production process, quality control is embedded at every stage. Inline sensors measure everything from ice cream viscosity to chocolate temperature, while human inspectors perform taste tests and texture evaluations on random samples. Microbiological swabbing, allergen verification, and weight calibration are also conducted routinely. Any deviation triggers alarms that pause the line until the issue is resolved. This level of scrutiny is necessary, not only to maintain consistency, but to ensure compliance with international food safety standards such as HACCP, ISO 22000, or BRC Global Standard. Once boxed, the finished Magnum bars are palletized and moved into cold storage. These industrial freezers maintain a stable environment at around -25 degrees Celsius, critical for preserving the product's texture and preventing recrystallization. From there, refrigerated trucks equipped with temperature monitoring systems distribute the bars to regional depots, supermarkets, and convenience stores. The logistics chain is tightly managed to ensure the product remains frozen solid all the way to the point of sale. Interestingly, the entire Magnum production system is designed for modularity and scalability. Production lines can be quickly reconfigured to produce different flavors, bar sizes, or seasonal variants, thanks to programmable logic controllers and standardized mold sets. In larger plants, multiple lines may run in parallel, each specializing in a different SKU. Automation doesn't just improve efficiency, it reduces contamination risks and allows for extremely precise control over ingredient ratios, freezing rates, and coating thickness. What makes Magnum truly remarkable is how it bridges artisanal quality with industrial efficiency. Despite being mass-produced, each bar is designed to evoke the sensory richness of a handcrafted dessert. The sound of the chocolate snap, the creaminess of the core, and the exact melting point of the coating are all fine-tuned, using years of research in food science and process engineering. Even sustainability has entered the picture. Many Magnum facilities are now integrating closed-loop water cooling systems, solar-powered equipment, and blockchain-enabled traceability for key ingredients like vanilla and cocoa. This reflects a growing consumer demand for transparency and environmental responsibility, even in the indulgent world of frozen treats. It all begins with the foundational dairy mix, which forms the base for every pint. Ben & Jerry's ice cream is made from cream, condensed skim milk, liquid sugar, and egg yolks. These ingredients are sourced from dairy farms that are part of the Caring Dairy program, a sustainability initiative focused on animal welfare, environmental stewardship, and farmer livelihood. The cream and milk arrive at the factory in insulated tanker trucks, which are sealed and refrigerated to ensure freshness. Each delivery is tested on arrival for butterfat content, temperature, and microbial safety before being offloaded into large, refrigerated stainless steel storage tanks. Once approved, the raw ingredients are metered into blending tanks, where the liquid base is formulated. These tanks are equipped with high-shear mixers and homogenizers that ensure a uniform dispersion of fat and solids. Egg yolks are added not just for richness, but as natural emulsifiers, giving Ben & Jerry's its thick, custard-like body. Depending on the flavor being produced, this base mix may also include cocoa powder, pure vanilla extract, or natural flavorings, each added in precisely measured quantities under strict batch protocols. Every component is logged and traceable, complying with both food safety regulations and the company's transparency standards. Next, the liquid mix is pasteurized to eliminate potential pathogens. This is done through a continuous flow system, typically a plate heat exchanger, that rapidly heats the mixture to around 83 degrees Celsius for about 15 seconds. The mix is then cooled instantly to below 4 degrees Celsius and sent to aging tanks. These stainless steel tanks are fitted with slow-moving paddles to keep the mix from separating while it rests for a minimum of 4 hours, and often up to 12. Aging allows the milk proteins and emulsifiers to fully hydrate, improves the texture, and helps develop the desired mouthfeel in the final product. Once the mix has aged properly, it's time for flavoring and freezing. This is one of the most tightly controlled and choreographed stages in the process. The aged base is pumped into continuous freezers, large barrel-shaped machines that scrape, whip, and chill the mix simultaneously. In these machines, the mix is cooled down to about -5 degrees Celsius and aerated with tiny amounts of air. Ben & Jerry's is known for its super premium designation, which means it contains less overrun than standard ice cream. Overrun refers to the amount of air incorporated during freezing, and low overrun results in a denser, creamier product. The target overrun for Ben & Jerry's is around 20%, far below the 80 to 100% often found in cheaper brands. As the ice cream exits the continuous freezer, it is still semi-soft and ready for the next hallmark of Ben & Jerry's, the mix-ins. The brand's chunky identity relies on adding generous portions of solid inclusions such as cookie dough, fudge brownies, peanut butter cups, and nuts. These ingredients are pre-prepared and kept frozen or chilled to prevent them from melting or breaking apart during mixing. They're delivered to the factory in bulk containers and are inspected for uniformity and contamination. Depending on the flavor, the inclusions are automatically dispensed into the flow of semi-frozen ice cream using an ingredient feeder. This is a sophisticated auger system that evenly meters chunks into the product stream without jamming or crushing them. The swirl elements, like caramel ribbons, fudge streaks, or marshmallow sauces, are added through a separate injection system. As the ice cream flows through a special section of the filler pipeline, precision nozzles inject thick sauces in continuous streams or pulses depending on the design. This ensures even distribution without blending the swirls into the base. preserving the distinct streaks of flavor that fans love. With all mix-ins and swirls incorporated, the ice cream is now ready for packaging. The semi-solid product is pumped into pre-labeled pints using automatic piston fillers. These fillers are calibrated to deposit exactly 473 milliliters of ice cream into each container with minimal air pockets or overflow. The filling heads descend onto the pint cups with synchronized timing, and sensors detect the proper fill level. The filled pints are then sealed with a foil lid and capped by a high-speed lidding machine. A light pressure press ensures that the lid sits flush, followed by a tamper-evident heat band or film seal in some plants. From here, the pints travel immediately into a hardening tunnel, an ultra-low temperature environment often referred to as a spiral freezer or blast tunnel. Operating at temperatures around -40 degrees Celsius, this tunnel freezes the pints solid in under 30 minutes, using high-velocity air circulation. Quick hardening is critical not only for texture and shelf life, but also to prevent the inclusions from sinking or rising within the pint before solidification. The spiral hardener moves the pints upward or downward along a long helical path, maximizing contact time while minimizing floor space. Once hardened, the pints are conveyed to a packaging line where they are inspected, date-coded, and boxed for shipment. Vision systems and weight sensors perform final quality checks, verifying that labels are correctly applied. Seals are intact, and there are no underweight or overfilled pints. Acceptable pints are collected into cartons, which are stacked onto pallets by robotic arms. These pallets are wrapped in plastic film and stored in cold storage at -25 degrees Celsius while awaiting distribution. Distribution logistics are tightly controlled to preserve the quality of the ice cream. Temperature-controlled trucks transport the product to regional distribution centers, supermarkets, and scoop shops. Each truck is equipped with data loggers that track interior temperatures, and any deviations are flagged as potential compromise points. Even at the point of sale, Ben & Jerry's invests in branded freezers with specific temperature and airflow settings to preserve texture and flavor. While the process is highly industrialized, Ben & Jerry's maintains a close connection to its values. Fairtrade certified cocoa, vanilla, and sugar are used wherever possible. The brownie pieces come from Greyston Bakery, a New York-based social enterprise that employs people with barriers to employment. Many of the flavor developments happen in pilot-scale test kitchens, where new combinations are trialed in small batches before being scaled up. Once a new recipe is approved, the production team carefully adapts it to the factory setting, ensuring that the large-scale version retains the chunky, indulgent characteristics of the original. Clean-in-place systems are another critical component of the factory's operation. Between each production run, especially when switching flavors, the lines must be thoroughly cleaned to prevent cross-contamination. CIP systems flush the internal surfaces of mixers, freezers, pipes, and fillers with a series of hot water, caustic detergent, and sanitizing solutions. These cycles are automated and monitored by sensors to ensure complete sanitation while minimizing water and chemical usage. Factory workers and quality assurance teams play an essential role in the process. From ingredient reception to final packaging, trained personnel conduct sensory evaluations, sample testing, and equipment calibration. Every batch is logged, sampled, and stored for traceability. Flavor consistency is particularly important for a brand like Ben & Jerry's, where fans expect each pint of half-baked or cherry Garcia to taste exactly the same as their last. In recent years, automation and data analytics have further optimized the process. SCADA systems monitor real-time parameters like flow rate, temperature, and mixing speed. If a deviation occurs, alerts are sent to operators who can intervene before a quality problem arises. At the same time, this data is archived for trend analysis and continuous improvement initiatives. Despite all the technology, What sets Ben & Jerry's apart is the commitment to texture, flavor, integrity, and social values. Making a pint of ice cream that contains a half dozen different textures, swirls, and inclusions without compromising on any aspect requires not just precision, but passion. It's not merely about freezing cream and sugar, it's about orchestrating a complex ballet of ingredients, machinery, and people to produce something that brings joy in every spoonful. The process begins with the sourcing of raw ingredients, mainly fresh cream, whole milk, sugar, and egg yolks. Häagen-Dazs prides itself on using as few ingredients as possible, which means that the quality and consistency of each one is paramount. The cream and milk are typically sourced from regional dairy suppliers that meet strict quality and animal welfare standards. Upon arrival at the production facility, these dairy ingredients are pumped from insulated tanker trucks into temperature-controlled holding tanks. These tanks maintain the cream and milk at around 2 to 4 degrees Celsius to preserve freshness. Before they are cleared for use, samples from each delivery are sent to the on-site quality assurance lab for immediate testing. These tests measure fat content, microbiological safety, and protein levels to ensure the mix will deliver Häagen-Dazs's signature richness. Once the raw ingredients pass inspection, they are moved to large blending tanks equipped with high-shear mixers. These stainless steel vessels allow the controlled integration of the cream, milk, liquid sugar, and egg yolks. Egg yolks are particularly important in Häagen-Dazs formulations as they act as a natural emulsifier, helping to bind the fat and water components together into a smooth, stable emulsion. This use of real eggs is a hallmark of the brand's French-style custard base. In some flavors, pure vanilla extract or cocoa powder is added at this stage, depending on the batch being produced. Every ingredient is weighed and logged, and the entire recipe is controlled by a central PLC system that ensures each batch is blended to exact specifications. Following the blending step, the liquid mix is subjected to pasteurization. This critical food safety step involves rapidly heating the mix to about 82-85 degrees Celsius for 15 seconds using a plate heat exchanger. This kills off any potential pathogenic bacteria while preserving the functional qualities of the proteins and emulsifiers. Immediately after pasteurization, the mix is cooled to below 4 degrees Celsius and sent to aging tanks. These tanks, which are usually insulated and jacketed for precision cooling, hold the mixture for 8 to 24 hours. During this aging period, the proteins and emulsifiers fully hydrate and the fat crystals begin to form, a process that is essential to creating the dense, creamy mouthfeel that distinguishes Häagen-Dazs from other ice cream brands. Once aged, the mixture is ready to be frozen. The liquid base is pumped into continuous freezers, which are rotating barrel machines designed to freeze and aerate the ice cream simultaneously. Häagen-Dazs ice cream is notable for its low overrun, typically around 20% or less. This means that very little air is incorporated during freezing, resulting in a denser, heavier product. This contrasts with standard commercial ice cream, which may contain 100% overrun, effectively doubling the volume through air alone. The continuous freezer chills the mix to about -5 degrees Celsius while blending it with microbubbles of air to achieve the desired consistency. Once the product exits the freezer, it's in a soft serve state, thick enough to hold its shape but still pliable. At this point, any swirl ingredients, flavor pastes, or inclusions such as chocolate chunks or fruit pieces are added. Unlike brands that pack their products with multiple layers of mix-ins, Häagen-Dazs tends to focus on refined and restrained combinations. However, for flavors like chocolate chip or dulce de leche, ingredient feeders are used to incorporate solid components without damaging them or disrupting the flow of the product. These feeders use auger screws and synchronized timing to introduce the chunks or ribbons directly into the stream of semi-frozen ice cream. ensuring even distribution. After inclusions are added, the ice cream flows to the filling station. Pints, which are pre-labeled and stacked in a hopper, are automatically placed onto a conveyor system that moves them beneath piston fillers. These fillers are designed to deposit exactly 14 fluid ounces of product into each container. The fill process is timed perfectly to prevent splashing or overfilling, and sensors monitor the weight and height of each pint as it passes. After the pint is filled, a foil seal may be applied to help maintain freshness and reduce freezer burn. Then, the lid is placed using a robotic arm and lightly pressed for an airtight fit. From here, the pints are conveyed into a spiral hardening tunnel, a vertical, corkscrew-shaped blast freezer that rapidly brings the core temperature of each pint down to below -20 degrees Celsius. This freezing must occur quickly to prevent the formation of large ice crystals, which would ruin the smooth, dense texture. The spiral design maximizes surface area and airflow while minimizing the footprint on the factory floor. Depending on production volume and configuration, the tunnel can hold hundreds of pints at a time, moving them slowly along the spiral track for 30 to 60 minutes. Once hardened, the pints exit the tunnel and move into the packaging zone. Each pint is inspected for proper sealing, correct labeling, and visual defects. This inspection process may include optical scanners and machine vision systems that check for off-coloration, misaligned labels, or foreign material. Some facilities also use X-ray systems to detect any hard contaminants that may have entered during the filling process, particularly in flavors with inclusions like nuts or toffee. After passing inspection, the pints are grouped and boxed into secondary packaging, usually corrugated cardboard cases containing 6 or 8 units. These boxes are sealed and barcoded for traceability, then stacked onto pallets by an automated robotic palletizer. Each pallet is wrapped in shrink film to stabilize it for cold storage. The wrapped pallets are moved to a deep freeze warehouse area kept at -25 degrees Celsius, where they await transportation. Distribution of Häagen-Dazs products follows a tightly regulated cold chain protocol. Reefer trucks, equipped with real-time temperature tracking, pick up pallets and deliver them to regional warehouses or retail outlets. Any temperature breach in the chain is recorded and flagged, as a product exposed to temperatures above -12 degrees Celsius for prolonged periods risks partial thawing and textural damage. The robust cold chain logistics ensure that every pint maintains the same texture and quality, whether it's eaten in Paris, Tokyo, or New York. Throughout this entire process, food safety and quality assurance teams are deeply involved. Every step, from ingredient reception to final shipping, is documented under a comprehensive HACCP plan. Daily samples are taken from every production run and stored for shelf life testing. Sensory panels evaluate texture, flavor, aroma, and meltdown properties. Microbiological testing is conducted regularly to verify sanitation effectiveness. In the event of any deviation from standards, production can be halted and equipment cleaned using automated clean-in-place systems. Häagen-Dazs also invests in sustainable practices wherever possible. Many of their dairy farms operate under environmentally conscious guidelines, and the brand continues to explore renewable energy options for its manufacturing facilities. Water use, waste generation, and energy consumption are tracked and reported as part of the company's larger environmental footprint goals. What's remarkable about Häagen-Dazs' production process is how it maintains artisanal quality while operating at global scale. Every pint is the result of a finely tuned interplay between ingredients, equipment, and process control. The use of real eggs and cream, the low overrun, the gentle treatment of inclusions, and the quick freezing spiral tunnel all contribute to a final product that feels indulgent and rich with every bite. And while machines do much of the heavy lifting, people remain at the heart of the operation, checking batches, tasting new formulations, maintaining equipment, and ensuring that every pint lives up to the brand's heritage. In an age where so much food is optimized for speed and cost, Häagen-Dazs stands out by elevating the basics. It doesn't chase novelty for novelty's sake. Instead, it doubles down on purity, richness, and consistency, transforming simple ingredients into something decadent through a meticulously managed production process. Chocolate begins its life not in the factory, but on the tropical cacao farms that line the equator. These farms are located in countries across West Africa, Central and South America, and Southeast Asia, with Ivory Coast and Ghana among the world's top producers. The climate in these regions, hot, humid, and with rich, well-draining soil, is essential for the cultivation of Theobroma cacao, the tree that produces cacao pods. Each pod contains 20 to 50 seeds, known as cacao beans, surrounded by a sweet, pulpy, white fruit. These beans are the raw foundation of all chocolate products. The cacao harvest is entirely manual. Farmers use machetes or curved knives attached to long poles to carefully cut ripe pods from the trees without damaging the branches. A single mature tree may produce between 20 and 30 pods per year, and since cacao does not ripen all at once, harvesting occurs continuously over several months. Once harvested, the pods are collected in piles and opened by hand using machetes. The beans, still coated in sticky white pulp, are scooped out and prepared for fermentation, the first transformative step in the chocolate-making process. Fermentation typically occurs on the farm or at centralized collection centers. Though it might sound like a simple resting period, fermentation is a critical and highly sensitive step that chemically alters the beans and begins to develop the flavor precursors of chocolate. Beans are placed in shallow, slatted wooden boxes or piled into heaps and covered with banana leaves. This environment encourages the growth of natural yeasts and bacteria that convert sugars in the pulp into alcohol and acids. As the temperature rises, often reaching 45 to 50 degrees Celsius, the bean's internal structure changes. Enzymes are activated, cell walls are broken down, and bitter polyphenols begin to transform into the complex flavor compounds that will later give chocolate its signature taste. Fermentation typically lasts 5 to 7 days, during which the beans are turned or mixed once or twice a day to ensure even microbial activity and oxygenation. This step is closely monitored, as under-fermentation leads to bland or vegetal flavors, while over-fermentation can introduce off notes like mold, vinegar, or excessive bitterness. Many large chocolate manufacturers, even though they don't ferment beans on site, have established quality programs with their cacao suppliers, training them in fermentation control, and even requiring on-site testing of pH and temperature during the process. Once fermentation is complete, the beans are spread out to dry. Drying can be done on large tarpaulins, bamboo mats, or raised wooden platforms under the sun. Industrial cacao processors often prefer sun drying, which can take 5 to 10 days, as it produces cleaner, more natural flavor profiles. During drying, the beans are turned regularly to ensure even moisture loss. The goal is to reduce the moisture content to around 6%, 7%, a safe level that prevents mold and microbial growth during storage and transport. At this point, the beans are still covered in their thin, brittle shells and have taken on a dark brown color, with their signature earthy, chocolatey aroma starting to develop. The beans are carefully bagged in burlap sacks, usually 60 to 65 kilograms per bag, and labeled with origin information including country, region, farm or co-op, and processing dates. These bags are then consolidated for export. Exporting cacao beans requires extreme care and logistics planning. Moisture, heat, and exposure to foreign odors can degrade the beans before they even reach the factory. To prevent spoilage, the sacks are loaded into dry, ventilated shipping containers, often lined with insulating material or desiccant packs to control humidity. During long overseas shipments, particularly by sea freight, the cargo is monitored using data loggers that track temperature and humidity. If the beans are exposed to extreme conditions, entire shipments can be rejected by the receiving chocolate manufacturer. When the beans arrive at the chocolate factory, usually located in Europe, North America, or Asia, they undergo a rigorous intake and inspection process. This is where industrial chocolate production truly begins. First, the bags are unloaded into a receiving area where samples are drawn from each lot and taken to the quality control lab. Here, technicians measure moisture content, check for mold or insect damage, and grade the beans based on size, color, and cut tests. Cut tests involve slicing a sample of beans lengthwise and examining the cross-section. Properly fermented beans will have a uniform, slightly purplish interior with no signs of germination or off colors. Beans that meet the manufacturer's standards are then approved for processing. The sacks are emptied into large hoppers that feed the cleaning and pre-processing line. At this point, the factory begins to function much like a grain mill, sorting, cleaning, and prepping the raw material for transformation. The first stage is mechanical cleaning. The beans pass through vibrating screens and air jets that remove sticks, stones, dust, string, and other foreign materials. Magnetic separators remove any stray metal particles picked up during harvest or shipping. After cleaning, the beans are often sorted by size. This is an optional step, but many high-end chocolate makers insist on sorting to ensure that beans of uniform size are roasted together. Uneven roasting is a major risk if large and small beans are mixed, as the small beans may burn while the larger ones under-roast. Before roasting, the factory may also conduct a dehumidification step, particularly if the beans arrived slightly above target moisture. Large rotary dryers or low-temperature ovens are used to bring the beans into precise moisture range, often 5%, 6%, to prepare for optimal roast conditions. This is all monitored through programmable logic controllers that track time, temperature, airflow rate, and moisture loss in real time. With the cacao beans now thoroughly cleaned, dried to precise moisture levels, sorted by size, and passed through rigorous quality inspections, the chocolate production process enters one of its most transformative and delicate phases: roasting. This step marks the moment when raw agricultural product begins to develop the hallmark sensory properties of finished chocolate: aroma, depth, bitterness, sweetness, and complexity. Far from being a simple baking process, industrial chocolate roasting is a finely tuned science that must balance heat, time, air circulation, and even bean origin to unlock the flavor potential locked within the bean's cellular structure. The roasted profile of chocolate is not one size fits all. It varies greatly depending on the origin of the beans, the desired flavor profile of the final product, and the style of chocolate being produced, whether it's milk, dark, or even single origin specialty bars. As such, chocolate factories have roasting protocols tailored to each bean variety and product type. These protocols are logged as roast profiles, charts that map temperature over time, often broken into phases: drying, browning, and development. Each phase requires precise thermal input and airflow to extract the right flavors without burning or flattening the bean. Industrial chocolate factories use several types of roasters depending on scale and product goals. The most common are batch drum roasters and continuous roasters. Batch drum roasters, similar in design to coffee roasters but much larger, feature a rotating cylindrical drum made from stainless steel. Beans are loaded into the drum, which rotates over direct or indirect heat, with hot air circulated through the drum chamber. Temperature sensors embedded in the drum monitor the bean mass, ambient air, and exhaust temperatures simultaneously. Factory operators can adjust drum speed, airflow rate, and burner intensity through PLC-controlled interfaces to manage the roast curve. Roasting typically begins at a lower temperature, around 100 degrees Celsius, to drive off any remaining surface moisture. This is the drying phase and usually lasts for 5 to 10 minutes. The beans then enter the browning phase, where the Maillard reaction begins. This is the chemical process that causes amino acids and reducing sugars in the beans to recombine and form hundreds of flavor compounds: nutty, roasted, caramelized, and acidic notes that are essential for chocolate's complexity. This phase is carefully controlled, usually taking another 10 to 15 minutes, with bean temperatures rising to 120-140 degrees Celsius. The final stage of roasting is known as development, or the finishing phase. Here, the beans are brought to their final internal temperature, typically between 135 degrees Celsius and 150 degrees Celsius, depending on the desired flavor profile. This phase is brief, often just 2 to 5 minutes, but it's critically important. Too little development, and the flavor may be grassy or underwhelming. Too much, and the chocolate may taste burnt, acrid, or flat. Advanced factories use real-time infrared cameras and bean temperature probes to monitor this phase with incredible accuracy, sometimes recording temperatures at 1-second intervals. After roasting, the beans must be cooled quickly to halt the cooking process. This is usually achieved in a dedicated cooling drum or tray system, where ambient or chilled air is blown across the beans using high-speed fans. Cooling not only stops the roast, but it also firms up the bean shell and prevents steam buildup, which could cause condensation or spoilage during storage. At this point, the beans are dark brown, fragrant, and brittle, but they still contain their outer shells, a thin, papery husk that must be removed to access the valuable interior, the cacao nib. The next phase is known as winnowing. Winnowing is a mechanical process that cracks the beans open and separates the lightweight shells from the dense nibs using a combination of crushing and air classification. In a large-scale chocolate factory, beans are first passed through a pre-cracker or roll crusher, which breaks them into fragments of varying size. The cracked mixture is then fed into a winnowing chamber, often a series of vertical air columns or vibrating conveyor belts, where calibrated air jets or suction systems separate the heavier nibs from the lighter shells. The airflow is precisely tuned so that the nibs fall to the bottom collection bins while the husks are drawn upward into separate waste hoppers. The result is a batch of pure cacao nibs, dark, rich, and packed with flavor and cocoa solids. These nibs are now ready to be transformed into chocolate liquor, not an alcoholic beverage, but a thick, paste-like substance made from finely ground cacao nibs. This is where the chocolate truly begins to take shape. To produce liquor, the nibs are passed through industrial grinders known as pre-refiners or impact mills. These machines use either rotating steel blades or stone rollers to shear the nibs into smaller and smaller particles. As the nibs are ground, frictional heat causes the cocoa butter inside to melt. This transforms the mixture from a coarse, gritty powder into a flowing paste with a smooth, velvety texture. The grinding process typically reduces particle size to around 80 to 100 microns during this first stage. From here, the liquor is either held in heated tanks for further processing or sent directly to the next grinding phase, refining. Refining is the step where particle size is further reduced to achieve the smooth mouthfeel expected from high-quality chocolate. This is performed using 5-roll refiners or ball mills. 5-roll refiners consist of 5 horizontally stacked steel rollers, each rotating at a different speed. The chocolate liquor is fed into the gap between the rollers, which progressively shear the particles down to between 15 and 25 microns. At this size, individual cocoa and sugar particles are too small for the tongue to detect, giving chocolate its creamy texture. In factories producing sweetened chocolate, sugar is added during this refining phase. The sugar, already pre-milled to ensure consistent granule size, is blended with the chocolate liquor to form what's called a chocolate crumb. Depending on the recipe, milk powder, vanilla, lecithin, and other ingredients may also be added at this stage. These additions are carefully weighed and dosed using automated batching systems, which ensure that every batch conforms to a master formulation. After refining, the chocolate mass still feels dry and powdery. To turn it into a cohesive, pourable liquid with a smooth finish and stable flavor, it must undergo conching, a prolonged mixing and aeration process that can last anywhere from several hours to multiple days. Conching takes place in large heated vessels fitted with rotary arms or heavy granite rollers. The goal of conching is threefold: to develop flavor by oxidizing volatile acids, to smooth texture by distributing fat uniformly, and to improve viscosity by reducing moisture and undesirable compounds. The conching process is controlled in phases: dry conching, where the paste is crumbly and thick; plastic conching, where it softens and flows; and liquid conching, where the mass becomes fully fluid. Each conching profile is custom tailored to the specific chocolate type being produced. Milk chocolate, for instance, requires longer conching to balance milk solids and sugars, while high percentage dark chocolate may be conched shorter to retain more of its natural acidity and origin flavor. Throughout conching, temperature, shear force, and oxygen flow are all regulated. Some factories utilize closed-loop conches with nitrogen blanketing to reduce oxidation, while others incorporate vacuum systems to pull out undesirable volatile compounds. This stage is monitored using inline viscometers and gas sensors, ensuring consistent output from batch to batch. At this point in the process, the chocolate mixture has reached a smooth, glossy, and richly aromatic state. It flows as a thick liquid, its flavors matured and balanced from hours of careful mixing, grinding, and aeration. The next phase transforms that liquid mass into a finished, stable form suitable for packaging and distribution. This involves cooling and crystallizing the cocoa butter within the mixture in a very specific way, a stage that requires precision and control over time, temperature, and movement. The goal here is to encourage the formation of the right type of crystal structure in the cocoa butter. Cocoa butter can solidify into several different crystalline forms, but only one of them results in a final product that has a smooth surface, sharp snap, resistance to melting in the hand, and a stable shelf life. To achieve this, the entire mass must be carefully tempered. Tempering is carried out in machines built for continuous flow and temperature control. These tempering units begin by first heating the mixture slightly above the melting point of all crystal forms, typically around 45 degrees Celsius. This ensures that any existing crystal structures are completely melted away. The liquid is then cooled gradually, usually to somewhere between 26 degrees Celsius and 28 degrees Celsius, depending on the specific type being produced. During this cooling, movement is maintained through stirring blades and flow channels, allowing the desired type of stable crystal to begin forming. Once enough of these seeds have developed, the mixture is gently reheated to a precise finishing temperature, usually just under 32 degrees Celsius. This final temperature is critical. It allows the seeded crystals to remain while eliminating the unstable forms that would cause bloom or textural issues later on. The flow, agitation, and temperature must be maintained within a very tight range. Modern tempering equipment uses inline sensors and feedback control loops to monitor these values in real time, ensuring the product is correctly tempered before it moves into the next station. From here, the tempered liquid is conveyed to the molding lines. These are high-speed, fully automated systems designed to pour precise volumes into molds of various sizes and shapes. The molds themselves are preheated slightly to prevent premature setting and ensure even flow. As the mixture is deposited into each cavity, vibratory tables shake the molds to remove any trapped air bubbles and ensure a perfectly even distribution. Once filled and vibrated, the molds are sent through long cooling tunnels. These enclosed, refrigerated belt systems gradually reduce the temperature in controlled stages, allowing the internal structure to set without cracking or warping. The airflow, tunnel speed, and humidity are all precisely calibrated to avoid moisture condensation on the surface, which could lead to dull or sticky finishes. Once cooled and fully solidified, the bars or shapes are released from the molds using a combination of mechanical pushes and short bursts of air. The finished items are then transferred onto conveyors that lead to the inspection zone. Here, vision systems scan each piece for defects, looking for uneven surfaces, cracks, color inconsistency, or any signs of bloom. Imperfect units are automatically ejected from the line for recycling. In many operations, these rejected items are remelted and retempered to be used again in the next batch. From this point, the finished product moves toward wrapping and packaging. The type of packaging depends on the product format, whether individual bars, boxed assortments, filled shapes, or bulk items for further processing. For single bars, wrapping lines are designed to handle high volumes per minute. Each bar is conveyed through a wrapping machine that cuts, folds, and heat seals the wrapper with high-speed precision. These machines are synchronized with the flow of the production line to prevent jamming, tearing, or misalignment. Packaging materials include metallized films, waxed paper, biodegradable foils, or composite laminates. These materials are selected based on the storage requirements of the product, the region's environmental regulations, and the shelf life goals. Many manufacturers also include oxygen scavengers or modified atmosphere sealing to enhance freshness, especially for filled products. After wrapping, individual bars or pieces are grouped into larger cartons or boxes by pick-and-place robotics. These machines identify product orientation, pick them up using suction or mechanical fingers, and place them into retail boxes, display trays, or bulk cases. The outer cartons are sealed, labeled, and pass through final quality control scanners that confirm weight, barcode accuracy, and expiration coding. Palletizing comes next. Stacked and secured cartons are placed onto shipping pallets according to loading patterns that maximize space efficiency and minimize stress on the bottom layers. Pallets are shrink-wrapped using rotating arms or heat tunnels, and then labeled with shipping codes, batch numbers, and destination data. The entire production record for each batch is digitally logged in the factory's quality control database. This includes source information for the raw ingredients, roasting and grinding parameters, conching durations, tempering temperatures, molding timestamps, and final inspection results. Should any issue arise downstream in distribution or retail, the system allows full traceability back to the moment each unit was created. Finished pallets are moved to climate-controlled storage zones. These warehouse areas are kept at stable temperatures, generally between 16 degrees Celsius and 20 degrees Celsius, to prevent melting, blooming, or flavor degradation. Humidity is also controlled, often under 60%, to protect the product and packaging integrity. Some products are stored under specific lighting conditions to prevent discoloration, particularly white and milk varieties that are more sensitive to UV exposure. Finally, shipments are released according to production schedules aligned with distribution needs. Orders are grouped by destination region, retailer, or distributor and loaded into trucks, shipping containers, or cargo planes. Temperature data loggers may be placed inside shipments to confirm that climate conditions remain within acceptable limits throughout transport. Though the product has now left the facility, its connection to the factory process is never lost. Retail complaints, test results, or customer feedback can all be traced back to the specific day, shift, and equipment used. Manufacturers regularly run shelf life simulations, flavor degradation tests, and mechanical stress analyses on packaged goods to validate the effectiveness of the process long after the final product leaves the line. Every stage, from raw bean to packaged bar, is designed not just for efficiency, but for repeatability and control. Factories producing chocolate operate like laboratories with strict protocols, while still honoring the craft behind each ingredient's transformation. This combination of technical discipline and sensory artistry is what makes industrial chocolate manufacturing one of the most exacting and fascinating operations in the global food industry. Once the finished chocolate leaves the factory, perfectly tempered, molded, cooled, and sealed in its final packaging, the industrial process doesn't come to a halt. A crucial final phase still unfolds, one that ensures the product not only reaches shelves in perfect condition, but also maintains its quality and integrity through transportation, storage, retail display, and eventual consumption. This extended phase is managed through sophisticated logistics, environmental monitoring, supply chain coordination, and continuous quality assurance practices. While this may seem like the back end of production, it is deeply integrated into how chocolate is made and maintained on a global scale. Immediately after production, the packaged chocolate is transferred into climate-controlled storage areas within the factory's distribution wing. These areas are tightly regulated to prevent degradation. The ideal temperature for storing finished chocolate is generally between 16 degrees Celsius and 20 degrees Celsius, with humidity kept below 60%. Above this humidity threshold, there is risk of sugar bloom, a white, dusty coating that forms when moisture causes sugar to dissolve and then recrystallize on the surface. Below this range, especially in dry climates, static electricity and brittleness can become issues, particularly for filled or aerated varieties. Storage racks are arranged to allow airflow between pallets. Each pallet is tagged with a unique identifier and scanned into the warehouse management system. This allows the system to track not only where each batch is physically stored, but also how long it's been in inventory, where it needs to go next, and whether it's awaiting any last-minute quality hold releases. Before a batch can ship, a final set of post-production tests is sometimes performed on a sample group. These tests may include accelerated shelf life simulations, where chocolate is exposed to varying environmental conditions in climate chambers to determine how it performs over time. Texture analyzers may test for brittleness or softening, while gas chromatography may be used to check whether volatile flavor compounds remain stable. Once cleared, shipments are scheduled for distribution. Whether headed to a supermarket distribution center, a specialty retailer, or international export, the chocolate must be loaded into transport systems that preserve the exacting conditions it was stored under. This can involve refrigerated or climate-controlled trailers, especially for higher-end varieties or filled products that are more vulnerable to heat. During warmer seasons, some companies delay shipments until nightfall or equip their pallets with insulation wraps to preserve temperature during brief exposure windows. Transport vehicles are often equipped with onboard temperature loggers. These small, battery-powered devices record environmental conditions every few minutes and are reviewed upon delivery to confirm that there were no unacceptable spikes in heat or humidity. If the data shows a breach, the receiving party may reject the shipment, even if the exterior packaging appears untouched. This level of accountability ensures that the integrity of the product is never assumed, but always confirmed. At the retailer level, chocolate continues to face environmental risks. Supermarkets and convenience stores may place chocolate in non-refrigerated aisles where exposure to lighting, fluctuating temperatures, and air conditioning vents can impact quality. To mitigate this, factory teams sometimes conduct in-store audits, either directly or through contracted merchandising specialists. These audits include checks on product placement, shelf temperature, rotation practices, and visible quality. Manufacturers also perform pull tests, where random samples are purchased directly from stores and sent back to internal labs for analysis. This helps determine if the product maintains its texture, snap, and flavor after weeks or months in the distribution system. These real-world results are fed back into the production process, helping engineers refine shelf life goals, tweak packaging barrier specifications, or adjust emulsifier ratios for better thermal resilience. Despite this rigorous system, the industrial process isn't rigid. Many manufacturers now build flexibility into their operations to support seasonal releases, new flavor experiments, and evolving consumer preferences. This includes small batch production lines within large factories that can produce limited runs of new recipes without interrupting mass-scale output. Even with these small lines, all the same steps: roasting, refining, conching, tempering, molding, wrapping are followed precisely, but in more agile formats. The long arc of chocolate production, from tropical farm to factory and beyond, is a story of transformation, precision, and protection. Each stage is critical, from developing flavor precursors during fermentation, to unlocking complexity through roasting, to achieving that final, glossy finish through proper tempering and cooling. It's not just about creating a product, it's about preserving it, tracking it, testing it, and delivering it across continents in exactly the state it was intended.